Good evening, all. Can you guys listen to me? Can you guys hear me right now?
Yes, ma'am.
Yeah, okay. There is no problem with the audio, right? Okay. So we'll begin today's live session, a problem solving session for the course Matlab programming for numerical computation. Hmm, Let me just check the time. We'll wait for like 1 more minute so that if there are more participants, we'll let them join. And we'll start the session by like 6:04, we'll start the session. Okay. Just wait for like 2 minutes. Session. Let's start the session. So this week we'll be discussing about linear algebra. We'll be trying to see how we can solve a set of linear equations. So this some we'll first, as we used to do in the previous sessions also, first we'll have a quick recap of what we did in the recording lectures. And then if you have any doubts, like conceptual doubts, you can just ask me then and there. And then we'll try to solve some problems that will be similar to the ones that you will get for the assignments. So this will be like a practice session so that that will help you solve your assignment questions. So to begin, first let's start with some basic of linear algebra. So you know how to create matrices. How to enter data into the matrices was already taught to you in the first 2 weeks of this course. So we usually start with the square bracket. You define the rows and then you put a semicolon, then it goes to the next line. So that's how you write the matrix. So then there is an important term which is called as the rank of a matrix. So for the rank of a matrix, this also I have covered in the previous classes, but I'll repeat it again here. So rank of a matrix refers to the number of linearly independent rows or columns. So here you can see it is a 2 rows and 3 columns, 2 by 3 matrix. And here you can see the row 2, 369. This row 2 is actually a multiple of the first row. That is, if you multiply R1, sorry, the row 1 by 3, you will be getting row 2. So here, how many independent rows do we have? So the only independent row is row number 1. Or else you can think in such a way that row number 1 can be obtained by dividing row 2 by 3. Okay, if you divide this row 2, just a second, let me just annotate. Uh, so you can also think in such a way that this R3, sorry, R2 can be divided by 3. you'll be getting R1. Okay. So that way also you can see how these are related. Even in that way also you can say that this is the only independent row. Okay. Otherwise, as per the definition that is given downwards, you will be saying that okay, R1 is the only independent row. In both the cases, the rank of this matrix is rank 1. Okay. Now moving on to the next matrix, you have like a 3 by 3 matrix. It's a 3 by 3 matrix. And here you have like row 1, row 2, row 3. And you can write R3 as a sum of R1 and R2. So if you sum these two rows, you will be getting the third row. In this case also, how many independent rows do we have? We have row 1 independent, row 2 also independent. But row 3 is a function of R1 and R2. So here the rank, that is the number of independent rows, is 2. Now taking the third matrix, this is also a 3 by 3 matrix. And here we can say that if R1, so this relation that is given here, R1 minus 2 times R2. Okay, let's just do an example here. So let's take this R1, 1 value minus 2 times R2, that is 2 multiplied by 0 is again 1. Again here 2 multiplied, so I'm taking this element minus 2 times R2, minus 2 times, okay, this is minus 2, right? Now that's next element is 3 minus 2 times 2. This is again minus 1. So you can say that this R3 is a function of R1 and R2 in such a way. So finally what you'll be getting that the number of independent rows just R1 and R2. So hence the rank 2. Now going into the fourth example, this is an identity matrix. So in identity matrix, you can never write a row or a column as a function of other rows or columns. So that's an important property of identity matrix. So hence the rank is 3. That is, all 3 rows are independent. You can't write one row as a function of other rows. So here, hence we have the rank that is equal to 3. Is there any doubt here? Okay. Now moving on to the next slide. Just a second. Yeah. Now we'll see so if we have a set of linear equations here, just a second. Okay. So here you can see a system of linear equation. That is, you can see that is x1, x2, x3 is equal to 4, 2x1 plus x2 plus 3x3 is equal to 7, and 3x1 plus 4x2 minus 2x3 is equal to 9. So here you have like 3 equations. And what will be what is the objective? We need to find what is the value of x1, x2, x3 in such a way that all 3 equations are satisfied simultaneously. Okay, all 3 equations must be satisfied for a single set of x1, x2, x3. That is what we need to find out. So if we have like a Matlab problem, if we have a max problem like this, how do we solve like mathematically, how do we solve? So what you can do is you can just extract the coefficients of these variables. So here your variables is, you write the variable in a column matrix as x1, x2, and x3. Okay. And then you write your constant as a column matrix. Sorry, that is 4, 7, 9. Okay. Then you write the coefficient term. Coefficient is this. Okay. Or the term that comes before your variable. 2 here. Here it will be 1, 3, 3, 4, minus 2. So let's write that as a 3 by 3 matrix. So that is 1, 1, 1, 2, 1, 3, 3, 4, minus 2. Okay. So now we have got this equation. This set of equations has been converted into matrix form. Once you have converted it to matrix form, this will be in the format A x is equal to B. If you have an equation like this, Ax is equal to B, how do you find x? In maths, you would have learned that to find x, what you have to do you have to just find the inverse of A and multiply it to B. Okay. So that's how you find the solution. When you do this, you will be getting an x vector like this, and it will have some values that corresponds to x1, x2, x3. So that's how we mathematically find out. So before going and finding the actual solution, we need to understand that if the set of equation has a solution or not. Okay. So for finding that, what do we do is we need to find the augmented matrix. Just a second. To find the augmented matrix, what we do is So consider a system of linear equation which can be written in the form Ax is equal to b. Okay, a system like this. And A has mn matrix of coefficient, and X is a vector of unknowns, and B is a vector of constants. Then we need to create an augmented matrix. How do you create an augmented matrix? Augmented matrix can be made in, it can be like A comma B. So I'll tell you how this matrix looks like. So you already seen the A matrix, right? A matrix is 1, 1, 1, then 2, 1, 3, then 3, 4, minus 2. Okay. Now for the augmented matrix, here in this column, you write the, sorry, here in this column, you write the constant matrix. So that is, in the same matrix, you add one more column, 4, 7, 9, the constant matrix. So this whole matrix is called the augmented matrix AB. Now what you have to do is, you have to find what is the rank of the matrix A. That is, this alone is matrix A. Okay, so this is matrix A, and this is the augmented matrix. Let me call it as AB. Okay, we need to find what is the rank of the matrix A, and we need to find what is the rank of the matrix AB. So if you don't have to use your brains to do this, what you can do is, there is like an inbuilt Matlab command called as rank. Okay, it's called as rank. You have to just give in the matrix as an input. The Matlab will give you what is the rank of the matrix. So if the rank of matrix A is less than rank of the augmented matrix AB, then we say that the system has no solution. If we find that both the ranks of A and the augmented matrix is matching, and that is equal to, and that if it is matching, then it is a guarantee that you might have at least one solution for this problem. Okay, but if this number rank of A is equal to rank of AB, and that is equal to rank of unknowns. So here how many unknowns we have? Here we have 3 unknowns. Okay, so if rank of A is 3, if rank of AB is 3, and if it's a rank, if the number of unknowns is also 3, then we say that the system has a unique solution, which means x1 next to x3 can only have one set of solution, and that set is there. There is no more options that is available. Okay, if rank A and rank A and rank of AB is equal, and but it is not equal to the number of unknowns, in that case system will have infinite number of solutions, that there will be different set of x1, x2, x3 that will satisfy the system. Okay, so that is how you check when you get a system of equation. That is how you check whether you have a solution there or not. Okay, first you have to identify that, and then only apply any mathematical methods to find the solution for x1, x2, x3. So once we have done this, let's look at what is the physical interpretation of these things. Just a second. Okay, so you know that linear equations are equations of straight line. Okay, so if we have like an equation where there is x1, x2, x3, this is a straight line in the 3D space. Okay, so let's see what is happening in a 2D space, because that is easy for you to like draw and understand. So this is a 2D space. So there is left a variable x1 and x2. So there are like two equations given. So here you can see 1, 2, 1. So this will be the Ax is equal to B format. Okay, this is your A matrix, this is your X matrix, and this is your B matrix or B matrix. Okay, so here let's write the coefficients. That is 1, 2, 1, minus 1, and this is x1, x2, the unknowns, and the constants is 1, 4. Now let's find what is the rank of this matrix. So just give me a second. Let me just share Matlab. Okay, just a second. In case if I'm going fast, or if you need any explanation in between, please to ask me. Okay, uh, just a second. Okay, I hope you can see Matlab right now. So let's write the A matrix was just give me a second. Okay, the A matrix was 1, 2. A is equal to 1, 2, then semicolon, we have 1, comma, minus 1. Okay, and B, which is your constant, is a column vector of 1, semicolon, 4. Okay, now this is your A matrix you have. Let's create an augmented matrix. So augmented matrix, I'm calling it AB. is equal to A, comma, small b. You've got the augmented matrix. Okay, so this is the matrix and this is the augmented matrix. Now let me find what is the rank of A. Rank of A is 2. Now let me find what is rank of AB. Okay, that is also equal to 2. Now let's go and look at the theory that we had. Okay, so now rank of A is 2, and rank of the augmented matrix is also 2, and that is also equal to the number of unknowns. If that is the case, what is the solution that we have? We have a unique solution. And what is the solution? So solution is 3 comma minus 1. So if we need to find what the solution is, we can just go to Matlab again. And you can find what is INV inverse of A, multiplied by B. We will be getting 3 comma minus 1. So this is a unique solution for your system. There is only one solution. Okay. Now let's go to the second problem. So physical interpretation is it will be like two straight lines. So physical interpretation is there will be two straight lines. Okay, these are the two straight lines equation and it will exactly coincide at one point. So that is why it is called as just has a unique solution. Now we have another system where A is 1, 2, 2, 4 and B is 1, 4. So if you are trying to find the rank of these two metrics, what happens is you will be getting this case. Sorry, you will be getting this case where rank of A is less than rank of AB. Okay, I can just show you that also once. Just give me a second. Okay, now A is equal to 1, 2, semicolon, 2, 4. Okay, now B is equal to 1, semicolon, 4. And I have written the augmented matrix. Let me find rank of A. Rank of A is 1 and rank of augmented matrix is 2. So now this is the first case where we have no solution. So what is a physical interpretation? Physical interpretation means that these two lines are like parallel lines. They don't coincide anywhere. Hence, the system has no solution. Now we go to the third case. In this case, what happens is A and B, the rank A and the augmented matrix both has the same rank, but that is not equal to the number of unknowns. In that case, what you have is you have the two lines that is exactly coinciding with each other, and there will be infinite number of solutions. That is, the whole line you can take a solution. Any point, if you extract any point of this line, that will satisfy this equation. So that is meant by the system having infinitely number of solutions. Is this clear? Any doubts?
Ma'am, I don't understand.
Which one? The starting itself, do we have doubts here itself?
Yes, ma'am. There
Okay.
I not understand the unique solution concept.
Okay. The thing is, what do you call a solution is there should be a point that satisfies the first equation and there should be a point that satisfies the second. Like should be a single value that satisfies both the equation. Okay. There should be an answer such a way that x1 and x2, you give some value for x1, give some value to x2. That should satisfy both the equation. How does it satisfy? You can see this is an equation of straight line. Okay. Y is equal to mx plus c. Okay, I have got a message in the chat. I'll reply to that. Just give me a second. So here what happens is this is an equation to straight line, like y is equal to mx plus c. Okay, so you can write this line like this. If you plot the line, it'll be like this. Do you have any doubt how this line is plotted? Do you know, like, do you have a question that how did this become a equation of a straight line?
Yes, ma'am.
Okay, so what do we do is, so we have here, I'll just do one thing. Let me just annotate. Yeah. So here we have x1 plus 2x2 is equal to 1. And let's have this is like a x1, x2 is here on the y-axis and x1 I'm drawing it in the x-axis. Okay. This is a coordinate system. Like x and y, we have a coordinate. Now what do I do is if I need to plot the straight line of this, if you need to know what this line looks like, what do I do is I put x1 is equal to 0. Okay, then what will be x2? X2 will be equal to 1 divided by 2, isn't it? If to satisfy this condition, if x1 is 0, x2 is equal to 1 divided by 2. Now I do, uh, just a second. Yeah. Now what do I do is I put, uh, just why is my annotation not working? Yeah. Now I do x2 is equal to 0. This becomes x1 is equal to 1. Okay. Now there are two values that is satisfying this points, satisfying this equation, that is 0 comma half and okay, 1 comma 0. These 2 points satisfy this line. Okay, so to plot it, what I do is x1 is 0, x2 is half. So imagine here, this is where half is. Okay, this point is satisfied. Now x1 is 1, and so here if it is 0.5, I'm taking this to be 1. Okay, now we have got 2 points. Now to draw the straight line, what do? You just join this line. Okay, this is the equation of this line. Sorry, this is the graph of this line. Okay, this is how you get this line corresponds to x1 plus 2x2 is equal to 1. Any point in this line you take, I took a point here. Okay, this point will satisfy this equation. I take a point here, that will satisfy this equation. So every point in the straight line will satisfy this equation. Okay, that is what we meant by an equation of a straight line. Now what happens is, I'm telling there are two straight lines like this. There is one straight line like this, another straight line like this. There is a point that satisfies this equation, and there is a point that satisfies this equation also. So there is one value that will satisfy both the straight lines. What does that mean? It means that two straight lines should coincide somewhere. So if you take this point, 3 comma minus 1, 3 comma minus 1 is touching the first straight line, and 3 comma minus 1 is touching the second straight line also. And it is only touching at one point. That is what is meant by unique solution. If two lines are touching at only one point, then that is called as a unique solution. If two lines are not touching at all, what does that mean? There is no value of x1 and x2 that is satisfying both the lines at the same time. Okay, so if example, if you take two parallel lines like this point will only satisfy the first equation. This point will only satisfy the second equation. There is no point that will satisfy both the equations. Now, if you go to the third example, you know these two lines are like exactly coinciding with each other. If you have a doubt, I'll do this. I'll try to plot the straight line of this. Okay. So the value is, this is the coefficient matrix. So the equation was like this: x1 plus 2x2 is equal to 1, and 2x1 plus 4x2 is equal to 2. So this was the equation. Okay. Now let me find out if x1 is equal to 0. What is value of x2? x2 is equal to half. x2 is equal to half. Now, x2 is equal to 0. x1 is what? What is the equation of x1? X1 will be 1. Okay? Okay. Now, this is the line that I get. If I... yeah. So, this is the line that I get. So, this is 0 comma half, and this is 1 comma 0. Now, let us look at the next equation, this equation. Okay? Here, what I do is x1 is equal to 0. That makes x2 to be equal to 2 divided by 4. What is it? Half. Now, x2 is equal to 0. What is x1? x1 is 2 divided by 2. Is that 1? You're getting the same solution that we got before. So that line also is the same line. So it looks different. It's the same line. Okay. So both the cases, you're getting the same line. This means that if you take a point here that satisfies both the lines, if you take a point here that satisfies both the lines, so there are like so many points that will satisfy both the equations. So this is what is meant by the system has infinite number of solutions. Has that got cleared? Like, do you have further doubts?
No, ma'am.
Okay. Yeah. So this is like in a 2D space. What happens is if you have like x1, x2, x3, then this line is in a three-dimensional space. Okay, that is right now, if you're sitting in a room, imagine that there is a line in front of you. Okay, that will have three coordinates. That will have an x, y, and z coordinate will also be there. Okay, so if you have like x1, x2, x3, x4, it means that it is a straight line in a four-dimensional space. Okay, but it will be a straight line as long as you don't have any powers. Like if it is just x1, x2, x3, not x1 square, x2 square like that. If the power is one, then it will be an equation of straight line. Depending on the number of variable, the space will be getting bigger and bigger. It can be a three-dimensional space, four-dimensional space, and so on. But it will be an equation of straight line. Okay. Now, like there was a question, like have I answered that question? How does the second and the third matrix rank is equal to 1? Which question you're talking about? Is this example or do you still have your doubt? Okay. Mahit, can you reply? Can I move forward? Okay, we'll take up that question later then. I've not got any response. Okay, now going into the second thing. So first we thought about rank of a matrix, and using the rank we have reached an ability where to identify whether that question has a unique solution, if it has either one solution or if it has like infinite number of solutions. We are able to identify that right now. Now the other thing is there is something called as eigenvalues and eigenvectors. So this you would have also learned in maths. Eigenvalues and eigenmetrics vectors means if you have a vector A, there are certain eigenvalues in such a way that let A be an n by n matrix and x be a non-zero vector for which you will have Ax is equal to lambda x for some scalar value lambda. So to satisfy this condition, the lambda that we have is called as an eigenvalue of the matrix A, and the x that we have will be having eigenvectors corresponding to this lambda. Okay, so Ax is equal to lambda x for satisfying this condition. Lambda is equal to lambda, we call it as eigenvalue, and x we call it as eigenvector. We'll come to that. So mathematically, how do you find the eigenvalues and eigenvectors? So if you don't have access to Matlab, how do we do it? So this is by finding the determinant of a minus alpha a equal to 0. I'll give an example here. If you have a matrix like this, a 0, 1, 0, minus 2, 3, 4, you have to write a matrix like a minus lambda I. So lambda is unknown. The whole objective is find the value of lambda, find the eigenvalues. Okay, that is find the value of lambda. What do you do is you write the matrix A like this. So this is a matrix A. Then you subtract lambda times the identity matrix. This is the identity matrix 1, 1, 0, 0. So then, and you take the determinant. So this what you see is a determinant. Okay, let's keep it there itself. Now what happens? 0 minus lambda, minus 2 minus 0. So this is minus 2. 3 minus, this is what? Did I make a mistake? I think I made a mistake here. No, this has to be 3, right? Yeah, I think that has to be 3. Okay. Now this is 4 minus, yeah, so there is a mistake in the solution. So basically what will happen is you will have 0 minus lambda. So this is minus lambda. Then you have minus 2, then 3, and then you have 4 minus lambda. This is the matrix that you have. Now we need to find what is the determinant of this matrix. What is the determinant of this matrix? Minus 4, 4 minus lambda, uh, minus 2, 3 is equal to 0. So that is minus 4 lambda plus lambda square. This is what? Plus 6, right? Is equal to 0. Okay, now is there a solution for this? This is a quadratic equation. A quadratic equation will have two solutions. That two solution will, it means that it has two eigenvalues. There are two possibilities. So one there is E1, one there is E2. This is how we find you have to solve this quadratic equation and you will be getting two values, which means there are two eigenvalues for the system. So if you need to find using Matlab, what do you do is, just a second. Uh, Let me just clear all this. So the matrix is 0, -2, 3, 4. Just a second. So the matrix you have. So let A be equal to 0, -2, sorry, equal to 0, comma, -2, and then you have semicolon 3, comma, 4. Was this your matrix? Okay. Now to find the eigenvalues, there is an inbuilt MATLAB command which is called as EIG. Okay. EIG A. So this is having like the eigenvalues. This is like a complex number. Okay. So you have like eigenvalues like this. Okay. So this is how we find the eigenvalues. So that could be like, for example, if you have a matrix here, this matrix, let's see. And what is the eigenvalue of this matrix? That is 0, comma 5. So now we'll see what all can this EIG, inbuilt MATLAB command, do for you. Sorry, EIG. See, this is what the MATLAB command can do for you. So EIG finds the eigenvalues and eigenvectors. If you just give one output, that is, you call the EIG, you give the matrix as an input, and as an output, if you're only giving one variable, this will produce a column vector E containing eigenvalues of the square matrix A. So this is eigenvalue. First eigenvalue is 0, second eigenvalue is 5. If you're giving two outputs, that is, instead of writing, I write like this, okay? V, comma, vector, comma, value. I'm just giving two outputs like this. What will happen is I'll be getting I'll be getting two matrices like this. I'll be getting a matrix like this. I'll be getting another matrix like this. In the first matrix, what happens is this column corresponds to my first eigenvector. Okay, this column corresponds to eigenvector. And the second column corresponds to the second eigenvector. This is the second eigenvector. Okay. Now there will be a question by what are the corresponding eigenvalues. You remember there is like an equation like this, that is AX is equal to lambda X. So for a particular eigenvalue, there is a particular X. So for example, if I have two lambdas, lambda 1 and lambda 2, if I have two lambda values like this, then there will be a vector x1 that will satisfy lambda 1 x1. And then there will be an x2 vector that will satisfy the lambda 2 x2. Okay, there will be, if there are two lambda 2s, if there are two lambda, there will be two vectors. So the lambda, so this is the first vector, this is the second vector. Value corresponding to the first vector is the first diagonal element, and value corresponding to the second vector is the second diagonal element. Okay, so 0 is the first eigenvalue, 5 is the second eigenvalue. Corresponding to 0, we have this. Corresponding to 5, we have this. Okay, this is what this EIG function gives you. Is this clear how to find the eigenvalues and eigenvectors of a matrix? You can use the inbuilt function EIG. You will be getting eigenvalues as a diagonal entries, and the corresponding eigenvectors will be the columns, first column and the second column. Any doubts? Okay. If not, let's move on. Just give me a second. So that's how we find the eigenvalues and eigenvectors. So mathematically, this is how you can find the eigenvalues. Or else you can use the MATLAB B, comma D. You have to just give like two outputs, and then it will be EIG A. Okay. So rank of a matrix, so there is another definition for rank of a matrix. Rank of a matrix is equal to the number of non-zero eigenvalues it has. Okay. Number of non-zero eigenvalues. So here earlier we saw there are two eigenvalues, 0 and 5. How many non-zero are there? Only 5 is the non-zero value. So the rank is 1. Okay, that is another way to find out what is the rank of a matrix. Now there is something called as a condition number of a matrix. So condition number means that condition number of a matrix is a measure of how sensitive the solution is. So as I told earlier, this matrix means it's a system of linear equations and it has a solution. That is x1, x2, x3 has a particular value. So condition number gives you an idea how sensitive the solution are. Okay. So how sensitive the solution of a system of linear equation is to the change of the input data. So to find the condition number, this is the formula that you have. It is a ratio of the largest eigenvalue to the smallest eigenvalue. Okay, just keep this in mind. This is a ratio of the absolute value. Okay, so if there is a negative eigenvalue, you have to take the absolute value, which means you only take the magnitude. The negative sign will not be taken. So the condition number is actually the ratio of the maximum absolute value, the eigenvalue maximum minus divided by the eigenvalue minimum. And remember, you have to take the absolute values of this eigenvalues. The large condition number, if you mean that there is a large condition number, indicates that the solution of a linear system can be very sensitive to input data. If the condition number is close to 1, then the solution of this linear system is less sensitive to the changes of input data. So just give me a second. Okay. So there are different ways you can find the eigenvalues here. Once you have found the eigenvalues, you can just find the condition number. If you don't want to go this route of finding eigenvalues and then the condition number, then there is a Matlab command called as COND is a condition number, and I'll give you the condition number. This means this is a very high condition number. Okay. Very high condition number means the system is very, very difficult to solve. For a slight change in x1, x2, the system will be deviating very much. Okay. So this is a very high condition number. If you want to see how this function works, COND, you'll be seeing. So condition number with respect to inversion. Okay. This is a ratio of the largest singular value of x to the smallest. So basically, it is a ratio of the largest eigenvalue to the smallest eigenvalue. Last condition number indicate nearly singular matrix. It means that the system will be very unstable. Okay, nearly singular matrix. Singular matrices are not preferred. It will be very unstable, the solution. Now moving forward. Yeah. Now let's come to the major part of this session of this week. That is how to solve the system of linear equations. Okay. So far we saw that if we have a system of linear equation, the easiest way is you take the inverse of A multiplied by B. Another way is instead of calculating inverse, there is a Matlab operator that is backslash. This backslash does the same thing as inverse operator. Either you can write it like this, inverse of A multiplied by B, or else you can write A backslash B. Both will give you the same answer. Okay, this we have already done and we saw that this will give you a column vector which will have x1, x2, x3 corresponding to it. Now, there are like several numerical methods to solve this. So, to find solution for this system of linear equation, there are several numerical methods that are available, like Gauss elimination, Gauss-Seidel method, LU decomposition. So these are the methods that we'll be trying to cover this week. I'll show you the codes, how each of this method works. Okay. So this is a straightforward method, but numerically, how do you do it? So first method that we see is called as a Gauss elimination method. In the Gauss elimination method, the first thing you have to do is, if you've got a system AX is equal to B, first create an augmented matrix AB. Once you've created an augmented matrix AB, then you choose the pivot element. So pivot element, you can see AII is called as a pivot element. Basically, the diagonal entries of the A matrix. So that is called as a pivot element. Now using this pivot element, you basically using the diagonal entries of A, you should make the elements that are below to be zeros. Okay, using the elements create zeros in the pivot column. Okay, and then you will have to do some. So for doing that, you will have some row operations like this. Okay, once you have created the row operations, then then you will see that the metrics have got simplified, and then you can do back substitution. Okay, this might be like a bit difficult to understand, so I'll just show you with an example. So this is a system that we have. So let's write the A matrix. It is 1, 1, 1. So that is 1, 1, 1, 2, 1, 3, 2, 1, 3, 3, 4, minus 2. Now, what are the pivoted elements here? Now, first we have to make an augmented matrix. Sorry. So this is an augmented matrix. You have this is A and this is 4. Sorry. This is 4, 7, 9. This is an augmented matrix. Right? With the augmented matrix, first we have to find the pivot elements. So first we'll go by row. First we'll consider first row, then we'll go to the second row, and then we'll go to the third row. Okay. So first let's go to the first row. What is a pivot element? As I said earlier, pivot element is a diagonal entry. So this, sorry. Mm, So this is one pivot element. This is the next pivot element. This is the next pivot element. After that, there is no diagonal entry. So first what we do is, using this pivot element, we need to make this and this entry 0 using some row operations. How do we do that? What we can do is, this element is 1, right? Okay, this element is 1. So next what we can do is, if you write row 2 is equal to row 2 minus 2 times row 1. What will happen if I do this? Okay, let's take this. I've taken this as a pivot element, and this is row 2. This is row 2, right? Okay. Now I make row 2 is equal to row 2 minus 2 times row 1. So that will be 2 minus 2 multiplied by 1. That will be 0. Okay. 1 minus 2 multiplied by 1. That is minus 1. Okay. And 3 minus 2 multiplied by 1. That is plus 1. And 7 minus 2 multiplied by 4. That is 8. That is minus 1. So after this row operation, what will happen? You will be getting a matrix like this. After doing this, you will be getting 1, 1, 1, 4. Then it will be 0, minus 1, 1, minus 1, 3, 4, minus 2, 9. So this became 0. Now the same thing you have to make, and you have to make this 0. How do we do that? R3 is equal to R3 minus 3 times R1. Yeah, will you get this 0? If you do this, you will be getting this also 0. This will change accordingly. So doing that, what will happen? You will be getting these two zeros. So there is no other rows there. So this operation is done. Now we choose the next pivot element. Got a message. Pivot element should always be 1. No. Pivot element can be other values also. Okay. So what happens is, I'll come to that. Okay. Pivot element need not be 1 always. So the pivot element next is minus 1. Okay. So just give me a second. I'll just go back. See, what you have to do is, pivot element is always AII. That is whatever is the diagonal entry. It can be 1, it can be minus 1. Like, it could be any value. Okay. There is no restrictions like that. So you need to know what should be this term. So here earlier I used 2 here. So look at this formula here. If you look at this formula, earlier I had used 2. So this alpha was 2. Next I used 3. That is, this alpha was 3. How did I get these values? So this alpha ij, there is a formula that is given here. This formula, that is AJI minus alpha IA. Basically, this element here, so this element was 2 here, right? So that is 2 divided by AII is what? 1. Next alpha ij is 3 divided by, what is AII? 1. That is how I got this 2 and 3. Okay. In the next case, for example, in this case, this is the pivot element. And for the next operation, what will be my value? That is next alpha ij will be 4 divided by the pivot element. 4 divided by minus 1 is what? Minus 4. Okay. Likewise, you will be getting alpha ij's. And if you do this, using this alpha ij's, you have to do the row operation. You will be getting zeros.
Ma'am, this
Okay.
alpha ij formula holds good for every time.
Yeah. This formula is general formula. Just that which row you want to change, that number comes here, divided by the corresponding pivot value. So for this is the pivot value. This column, this is a pivot value. So it is 3 divided by 1. For this, it will be 4 divided by minus 1, because this is the pivot value for that. Okay. This alpha ij is a common formula. Understood? And this Rj and Ri will be the corresponding columns. Okay, so here what happened, this is R2. So you can see R2. Okay, alpha ij means it will be, So let's take it. So
we will
here,
always divide by suppose A11, A22, A33 that
yes,
way.
yes, you're right. Yeah. We'll be dividing it by the corresponding pivot elements, basically corresponding diagonal entries. Okay. So this, if I take j is equal to 2, so this is R2 minus, sorry, R2 is equal to R2 minus alpha I is equal to 1, j is equal to 2, R1. What is alpha 1, 2? That is A 2 comma 1 divided by A11. What is A2 comma 1? That is this value. Okay. That is 2 divided by what is A11? That is this value. 1. So that is equal to 2. That is how you got this value here. Okay.
Okay.
Yeah. So this is what you're basically doing. Okay. You can do this with pen and paper and see if you're getting the solution. Okay. Now I'll show you how to write the code for this. Because you understand there is a certain pattern, right? There is a certain pattern. There is like a, so if you see this JI means there is like a certain pattern in which you can code it easily. So let's see how we can do that. Just give me a second. So this is the code for Gauss elimination. Okay. First, what I do is I have to create the augmented matrix. So this is, let me just clear CLC. This is my, I'll just run this section. Okay. I got the A matrix and the B matrix. So you've got the A matrix and the B matrix, and then you create the augmented matrix. So this is the augmented matrix, how you create it. The augmented matrix is created. Now what you have to do is I have to find the corresponding alpha values. So let's take the first A11 as a pivot element. Well, the A1 as a pivot element, you need to make the second row and the third row zeros. So what I do is first I have to take the pivot element. Sorry, first I have to take the pivot element and then I take what is the alpha value. So the alpha value is what? That is AB2 comma 1 divided by AB11. Okay, this formula is exactly the same what we saw earlier. So the exact formula was, so just a second. Let me just annotate. So we had seen this alpha ij is equal to a j comma I divided by a I comma I. So here I value first initially it is 1. So what happens when j is equal to 2, we have a 2 comma 1 divided by a 1 1 1. Okay, 1 1. When j is equal to 3, you have a 3 comma 1 divided by a 1 1. Okay, so this is first alpha is AB2 comma 1 divided by AB11. Next is AB3 comma 1 divided by AB11. So the two alpha values exactly as per the formula. Now this is the other formula, that is R2 minus R1 alpha R1. Is this formula clear? So that is what I do. This is the second row, all the columns. So this is again the second row minus alpha times the first row. This is third row. Third row is equal to third row minus alpha times the first row. So this is the row operations. So first, after doing this row operations, so this is the AB. Okay, after doing this row operation, let's see what is happening. I'll just run this section. You will be getting this 2 zeros. Okay, is this part clear? Okay. Yeah, okay. The next part is you have to take the next pivot element. Now I have taken 2 as
Ma'am,
a pivot element.
so
Yeah.
for general formula, we can write like alpha always will be this alpha I plus 1 comma 1 by AB alpha I comma 1 I comma I. That will always stand.
Yeah, that is always true. Yeah.
Okay.
Whatever formula that I showed in that PPT, it's a general formula. That's always true. Okay.
Okay. So J will okay.
J will be the corresponding row you want to change. If I want to change the second row, J will be 2. If I want to change the third row, J will be 3. Okay. So now I've taken 2 as a pivot element. Basically, this is my pivot element. After changing this, this became my pivot element. That is the second diagonal element. Using the second diagonal element, what I have to do, I have to make this entry 0. Okay. So that is, for me, I have to only worry about J equal to 3 because J equal to 2 is the diagonal entry. Okay. So this is J equal to 3. Now, what is alpha formula? You remember this is a alpha formula, right? So alpha ij will be a 3 comma, now what is my I value? I value is a diagonal entries value. That is my second row, right? This is I. So a 3 comma 2 divided by ai. What is I? That is a 2 comma 2, right? So that is what this value is. ab 3 comma 2 divided by ab 2. That is your new alpha value. Now with that you have to change the third row. So third row is equal to third row minus alpha times the second row, because second row is the row where the pivot element is. Okay. So now when I do this, what happens? Let me just run this. Okay. Now, okay, let me just clean this also. Now what happened? Now this became 0. Now we can see it's like the main diagonal has some values. All the elements below the diagonal, all the lower diagonal values are 0. Once you have made the lower diagonal value 0, you have finished the major part of the Gaussian elimination. Now what we have to do is you have to find the value of x1, x2, x3. For that, what you do is this is called as a back substitution. Okay, how does this work? Okay, the technical meaning of back substitution is, this is a matrix, right? So this is in the form, if you take this part, this is A, and if you take this part, this is B, right? So this is, if you write it in the equation format, what will happen? Just a second. Yeah, in the equation format, it will become x1 plus x2 plus x3 is equal to 4. Okay, then x1 is not there, it is 0, the coefficient is 0. So then you have minus x2 plus x3 is equal to minus 1. And then you have minus 4x3 is equal to minus 4. These are the equations you have. Now we need to find the value of x1, x2, x3. How do you find out? First use this formula. And then you take x3 is equal to minus 4 divided by minus 4, that is equal to 1. You got value of x3. X3 is known. Now you take this formula. X3 value you already know. The unknown is x2. So minus x2 plus 1 equal to minus 1 means what? Minus x is equal to minus 2. Sorry, x2. Okay. And x2 is equal to 2. If I'm making any mathematical calculation mistake, just let me know. Okay. So x1 you know, x2 you know. Now we put it in this equation. That is x1 plus 1 plus 2 is equal to 4. What is x1 then? That is equal to 1. So now what we do, this is called as back substitution. First you did with the last equation, then the answer you apply to the second last equation, then the answer you apply to the first equation. So this is a back substitution method that you talk about. Okay, so now the answer is 1, 2, 1. Okay, let's see if that is what we get using this back substitution formula. The same thing, whatever I did can be written in a loop like this because there is a pattern to it. Okay, so this is how you write it. X3 is equal to third row divided by the AB 3 nth means 3 third row last value, that is this value, divided by AB33, that is this value. You will be getting 1. So likewise, these are the equation. Whatever I wrote mathematically, this is the Matlab way of writing it. Okay, now you can see there is a pattern to it. Because of that pattern, you can write a loop doing the same thing. If you have a doubt what this loop is doing, what you have to do is just take a screenshot and for every value of I, okay, just expand this formula. You will be getting exactly this lines. Whatever I have commented, right, you will be getting exactly this lines. Okay, so now after doing back substitution, what you get is, I'll just run this. Sorry, n is equal to 3. I forgot to run that. Let me look at the value of x. Yeah. Let me clear the annotation. Yeah. Now this is the value 1, 2, 1. Okay. If you have doubt, if this is the right answer, what you can do is, you know the A and B, right? Let's do inverse of A multiplied by B. You'll be again getting 1, 2, 1. So this is a solution. Okay. First you do Gauss elimination, make a lot of entries 0, then you do back substitution. That is a method, numerical method of solving this system of linear equations. Any doubts? Okay.
No.
If there are no doubts, let's move on to the next part. Okay. After Gauss elimination, we have something called as, just a second. Okay. After Gauss elimination, then you have LU decomposition. LU decomposition means L is a lower diagonal. So this is what is capital L and U means. L means a lower triangular matrix. U means upper triangular matrix. Okay. So as per this LU decomposition, every matrix, okay, every square matrix can be written as a combination of a lower triangular matrix and an upper triangular matrix. Okay. So how do you make this lower triangular and upper triangular matrix? So you remember that once you do this Gaussian elimination, you got a matrix like this, where all the lower entries are 0. So there is only elements in the upper triangular. Okay. So the matrix that you get after Gauss elimination, that matrix is the U matrix. That is the upper triangular matrix. Now you'll ask me, what is the lower triangular matrix? You remember you had like alpha values. By doing this formula, you got alpha values, right? If you're putting this alpha values to the corresponding matrix, you will be getting the lower triangular matrix. So this is what alpha 2, 1. What is alpha 2, 1? Alpha 2, 1 is A21 divided by A11. Okay, that you have to put it at the matrix A2, comma 1. Okay, so this is the second row, first column. So corresponding alpha value, whatever you calculated, just put it, like save it in a different matrix. So that is L matrix. So finally, what will happen is, for L matrix, all the diagonal entries are 1. Okay, and the lower diagonals will be the alpha values that you get from the Gauss elimination. So that will give you your L matrix. Okay, is this clear how this L and U matrix is formed? U matrix is what you observe or get from the Gauss elimination. The final matrix that you get, that is a U matrix. And you remember you have calculated alpha values to find that U matrix, right? That alpha values, if you put it, save it here and keep it like this, you will get the L matrix. Is that clear? Okay. Now the question is, okay, you did LU decomposition, you got the L and U. Now, how do you find the solution to this matrix? Solution to your system of linear equation. So this is how we do it. You remember you have this equation, Ax is equal to B. You already have Ax is equal to B. Okay. Now you can write A as a function of L and U is equal to B. Okay. Now what you do is, this is a bit complicated way. I'm just telling you, with LU decomposition also you can come to the same answer. Okay. You don't have to always go through this what you say, difficult route. Okay. You can just do Gauss elimination, or you can just find the inverse of the matrix. That is perfectly fine. But I'm telling you, with LU decomposition also, you can reach the same answer, x1, x2, x3. Okay. Now what you do is, this ux, I'm calling it a different variable name. Let me call this y. So this is Ly is equal to B. You know what is a lower triangular matrix? You know the B matrix, right? Now the only unknown is y. How do you find y? This is inverse of L multiplied by B. Or you can do, just a second, or you can do, L backslash B. This will give the same answer. You will get Y. Okay. Now what is Y? Y was UX. Okay. That is UX is equal to Y. You know, the upper triangular matrix, you know. Y also you found out from here. Now the only unknown is X. So X is nothing but inverse of U multiplied by Y. You will be getting your X1, X2, X3. Is this clear how we can find this X1, X2, X3 if you are given an L and U matrix? Okay, so remember in your question you are given that there is a matrix. Just sorry, I have a small throat problem. Sorry for like muting it in between. So in the question, you are given an L matrix and U matrix and corresponding B matrix, and you are asked to find your solution. How do you do it? You can write the formula as LUX is equal to B. UX, you can name it as a different variable. So first find the value of that variable. Okay, first find what is Y. That is Ly is equal to B. L is given to you, B is given to you. Y can be found out by inverse of L multiplied by B. Okay, now we found Y. What is Y? Y is Ux. So you can write Ux is equal to Y. What is X? X is inverse of U multiplied by Y. Y you found out from here, U was given to you in the question. So you get X1, X2, X3. Any doubts?
No.
Okay. Okay. Now this is Gauss elimination with partial pivoting. The idea is exactly the same, but just that every time when you do Gauss elimination, no, numerically when you do it, you might not reach to the answer because you remember you have to find alphas. In alpha, you are dividing it by the pivot element AII. So what happens is, what if your alpha II? What if your pivot element is 0? Okay, what if your one diagonal element is 0? Can you divide a number by 0? You can't do that, right? So every time blindly doing Gauss elimination will not help you to get the answer. So for that, you have to do partial pivoting before doing Gaussian elimination. Okay, so that is like this. Use row exchange to ensure that the absolute value of the pivot element is the largest element in the column compared to the bottom elements in the column. So that is if I have, so first what you can do is you have to exchange in such a way that your pivot value is a large value. Okay, it's not 0 or 0.001. Don't divide by such a number. Okay, because when you divide by such numbers, what happens is your solution will be diverging. You can't divide a number by 0, and dividing a number by 0.001, you'll be getting a lot of and that will again cause a lot of trouble for you. So don't do that. What you have to do is you have to arrange it in such a way that your diagonal entries, basically your pivot elements, are large values. So for that, what you do is first look at the matrix. When you looked at the matrix, you can see that, see, okay, only look at the A matrix, okay? This is an augmented matrix. Let me only look at the A matrix. That is this. Okay, you saw the A matrix. So in the A matrix, you can see which is a large value. You can see 4 is a large value. Okay, comparatively 4 is a large value. So this 4 has to come in the diagonal entry. For coming in making that in the diagonal entry, what you have to do is you have to exchange these two rows. Okay, when you exchange these two rows, it will become 1, 1, 1, 3, 4, 2, 2, 1, 3. Now again, you can see that the diagonal entries are 1, 4, 3. Can I make it even better? So just exchange these two rows. It becomes 2, 1, 3, 3, 4, 2, 2, and 1, 1, 1. Here your diagonal entries were 1, 4, 3. Here my diagonal entries are 2, 4, 1. Okay. This diagonal entry, anyway, you're not going to use it. So getting a high value here, it is not going to help you much. But this diagonal entry is very important because okay, this diagonal entry is very important because with this you're dividing these two numbers, right? So this is a better option. Compared to this and this is a better option. So what this partial pivoting is that you do some row exchanges in such a way that your pivot element is a large number. It shouldn't be zeros or it shouldn't be like what you say, like, and also it should be the absolute value. Okay, we're not bothered if the number is negative or positive. We just don't want like small values to it, because when you're dividing a number by a small value, you'll be getting a large value, right? And this will lead to numerical instability as we progress. So this is the reasoning. Partial pivoting we do because to reduce error caused by round-offs or computational errors. Otherwise, we encounter a program problem such as division by zero or a very small number. Okay, is this idea clear? Now I'll just show you how to do this Gauss elimination in Matlab. So this code we have already seen. Okay, so this is A, B. We made the augmented matrix. Number of unknowns is 3. Now this is the partial pivoting part. Okay, you are exchanging columns. So for exchanging columns, what you have to do is, rather than rather than like looking like visually doing it, what you can do is you can just save the first column. Okay, save the first column. See which is the maximum value of the first column. So what this val and idx does is that val will solve the maximum value of the column, and idx will store the which index that maximum value happened, whether it is first value, second value, or the third value. This idx will store that. So based on that, what we do is, now I have to exchange the first row. Okay, so the whole thing was I had a row like this. I have like 3 rows like this. Now I am exchanging like this column because I am looking at the pivot element 1, 1. Okay, this element has to be highest. Okay, so for that, what do I do is I save the first column. So this is call 1. I save this as call 1. Okay, in call 1, I check which is the maximum value. Is this the value? Is this the value? Or is this the value? I check. And whichever index is, imagine that this is the highest value. Okay, so here IDX will be saved as 2. Now what do I do is I need to exchange between these 2 rows. If that is the case, what will happen if I simply exchange this value? If I write R1 is equal to R2, what will happen is this R1 will be written by R2, and whatever info was there in R1 will be overwritten. Okay, R1 is lost now. I can't exchange it back. If I can't write R2 equal to R1, because R1 is lost, it has been already replaced by R2. So now what I do is I use a dummy variable. So that is I first write, before exchanging, I write dummy is equal to R1. Now the value of R1 is stored here. Then I write R1 is equal to R2. Now I can write R2 is equal to dummy. Now, did the exchange happen properly? Did you guys understand this part? Or should I explain it again? Okay. If directly, if I write R2 equal to R1, so just imagine that I have 1, 2, 3, 4, 5, 6, and 3, 2, 1. Yeah, just I'll explain it again. Just give me. I'll explain it again with an example. Imagine I have a matrix like this. Okay. 1, 3, 2, 4, 5, 6, or 2, 1, 0. Okay, imagine I have a random matrix like this. Now what I do is I want to make this value highest. Among this column, this value should be highest. 1, 4, 2, which is highest, this is highest. I want this 4 to come here. Okay, so for that, what I do is I extract this one as column 1. This is what this code does. I extract the first column. Now what I do is I find what is the maximum value. Okay, now the maximum value will be 4. So val will be saving 4, and IDX will be index of it. Index is, it is happening in the second index. So IDX is 2. Now what I do is, if I simply write R1 is equal to R2. Now what will be my A matrix? A matrix will look like this. Okay. 4, 5, 6, 4, 5, 6, 2, 1, 0. Okay. Now if I write R2 equal to R1, basically I want to exchange this two, right? R2 equal to R1. Will anything change? Because right now we can see that both my rows are 4, 5, 6, 4, 5, 6. I lost my R1. Okay, R1 data, I have lost it because I've got it overwritten. Now what I do is, so this is not ideal. Okay, I lost my R1. Now I can't write R2 equal to R1 because R1 value is not there with me. So instead of going this route, I do a different route like this. Before overwriting, I save the value of R1 in a variable. So that is called as dummy. I write R1. Dummy is equal to R1. Now the value of R1 is saved in dummy. Then I write R2 is equal to R1. So that will give me this one. Oh, sorry, R1 is equal to R2. That will give me this one, 4, 5, 6, 4, 5, 6, 2, 1, 0. Now I write R2 is equal to dummy. Now what will happen? This 4, 5, 6 will change. Instead of that, I'll have dummy. Dummy is what? R1. That is 1, 3, 2. Now, did this get exchanged? These two rows got exchanged here, right? 4, 5, 6, 1, 3, 2. Did you understand why I'm using this dummy variable?
Yes, ma'am, to store the.
Yeah. I don't want it to get overwritten. So first in the dummy variable, I store the first row and then I exchange the rows. Then to whichever row I want to exchange. So that is having this IDX index. I save the dummy variable. Now the row exchange has successfully happened. So once I have changed the row index, I do the Gauss elimination. This is a Gauss elimination. Okay, there is nothing changed there. A11, I can calculate alpha, and using alpha, I make the lower element 0. Now there another thing is there. For my LU decomposition, what I do, I save the alpha value in the matrix L. Okay, I save alpha I comma Li comma 1 to be, sorry, Li comma 1 to be the corresponding alpha value. Okay, now I go to the second pivot element. For the second pivot element also, I need to make sure if this is the highest value. So for that, again, I do the row exchange. So first I extract the second column. I am only worried about the second column and that too, only this A2 to end means I am only worried about what is happening here. That is 2. Among this 5 and 1, this pivot element should be the largest. I'm not worried what is happening on the top because I'm not going to divide this numbers with my pivot element. I'm only going to divide the lower values, right? So among this sub like 5 and 1, I need the pivot element should be to be the largest. So I exchange A2 to end. Basically, these two elements and the second column. Again, I find what is the maximum. And before exchanging, I save it in a dummy variable. Now I exchange. Now to whatever I exchanged, I redefine my dummy variable. Okay, I resubstitute my dummy variable. Now again, the row exchange has been done. Again, I do the Gauss elimination. Done. The Gauss elimination part is done. The same formulas. I find alpha. I make all the lower entries 0. I save the alpha value in the matrix L. It becomes my lower diagonal matrix. Okay. Now I do the back substitution, just like I did earlier for Gauss elimination. So the only difference between Gauss elimination with partial pivoting is before doing any operation with the pivot element, make sure that is the highest. Make sure that is the highest value. Make sure that you're dividing the lower value, the lower elements, the whatever is there in the lower rows by a higher value, a large pivot element. Okay. So that is what is decided. I'll run this code for you. Just a second. Second, I've got 2 comments. Okay. I'll just run this. And if I look what is the x, y, z, it is again 1, 2. So if you want to see how this element looks like, let me just do one thing. I can do it by section to show you the difference. So this is your AB. Okay. Now after doing this, This is your AB. So earlier in the AB, the maximum element was 3. I would like to have 3 here. Okay. Now what I do, I exchange, it became 3, 2, 1, 4, 1, 1. Okay. This basically this row and this row I exchanged. Then I do the pivot, the Gauss elimination. It became 0, 0. Now, which is my next pivot element? That is 1, 6, 6, 7. Among this two, 166 and 0 minus 0.33, which is the highest, this is the highest. Okay, I'm only worried about the absolute value. I'm not worried about negative or positive. I'm only worried about absolute value. This is the highest. So ideally, it should in exchange. Okay, let me again do the exchange operation, whatever is there, and I'll see what will happen. Okay, let me see what the AB looks like. Yeah, AB hasn't changed because this is the highest element, so this hasn't changed. Now again, I'm doing the Gauss elimination. Again, let me look at AB. You can see this element became 0. Now it is back substitution. Okay. You first use this equation. With that value, you find this equation. And with that value, you solve this equation. Is this clear? Any doubts? Okay. If not, let's move forward. This method is called as a Gauss-Seidel method. This might be a bit tricky for you to understand how this formula came. Okay. It might be a bit tricky to understand. So, see, this is like if you have seen the previous week, we had seen how to solve this, how to find the square root of 2. That's an iterative method for finding square root of 2. So what do you do is, you first start with an initial guess value. You substitute that initial guess value in the formula, you'll get a new guess value. Again, you substitute the new guess value, again, you'll get a new value. So it's like a cycle. Okay, you start with an initial guess, you keep on getting new values, and then there is a convergence criteria. Once you reach a convergence criteria, you'll get to that solution. So I'm not going to the technicalities of this formula. So this is a formula. So if you have a matrix A, okay, and if you have a matrix B, and if you need to find what is the x value, that is a unknown value, this is a formula that to be applied. This is like an iterative method. I'll tell you how to do this iterative method. Mathematically, this is what it's doing. So imagine you have a system like this. Okay, x1 plus 2x2 is equal to 1. x1 minus x2 is equal to 4. Just give me a second. Okay, so if you have a system like this, how I do this is first, using the first equation, I make a formula like this. I'll write x1 is equal to 1 minus 2x2. I can take this to the other side, right? So it becomes 1 minus 2x2. And this is an equation for x1. From this, I make an equation for x2. x2 is equal to, I take this to the other side. Or else, yeah, I can take this to the other side and x2 to this side. So x2 is equal to minus 4 plus x1. Okay. So from this, I got an equation for x1 is equal to, I write an equation. From here, I write an equation as x2 is equal to. That is these two equations. Okay. Now, as the problem begins, I'll assume a value for x1, x2. Let it be 0, 0. To begin with, I'm taking value to be 0, 0. Now, what happens? When I put 0 here, I'll get a new value of x1. Okay. Now, with the new value of x1, I'll substitute it here. Okay. I put, when first iteration, my x2 value is 0. That is my initial guess. I apply it here. I get the new x1 value. The new x1 value, I apply it here. I'll get the new x2 value. Now the new x2 value, again apply it here. So the cycle is like this. Okay. From here, you get here. And from here, you go here. And okay, let me just clear all the drawing. Okay. So you start from here. Okay. From here, you get this value. From here, you put this value here. And from here, you will get this value. And this value, what do? You again put it here. It is like a cycle. So you start with an initial guess of x2, you get new value of x1. Okay. From new value of x1, you substitute it here, you get new value of x2. Again, put the x2 value here, and this goes as a cycle. When do you stop the cycle? You stop the cycle when you finally find that x1 values in subsequent iteration, that is xi plus 1 in xi plus x1, I plus 1, I plus 2. Like basically in the subsequent iteration, you will find that the x1 value is almost constant. And x2 value is also constant. If you find that even if you do any more iterations, if you find that x1 value, x2 value is not changing, then this solution has reached to a convergence. That constant value that you have got is the answer for this equation. X1 and x2, that is the answer for the equation. Okay. Now what I have done is from this first equation, I wrote x1 is equal to, from the second equation, I wrote x2 is equal to. I can do the vice versa also. That is, from the first equation, so from this equation, I am taking x1. x1 is equal to, and from this equation, I am writing x2 is equal to. Okay. If that is the case, what will happen? If that is the case, I can write x1 is equal to 4 plus x2, and x2 is equal to, from this equation, it will come. Okay. So that is why this half is coming. This has to be divided, right? When you take it to the other side. Now what happens? You assume initial value of x2. Okay. From that, you will get x1. From x1, you substitute it here, you will get x2. Again, you give back the x2. Like that, it goes on. Okay. It's according to you from which equation you want to take x1 and which equation you want to write it for x2. But there is something called as numerical stability. Okay. So as you can see here, so I'll just show the difference of these two problems. Okay. Uh, just a second. Okay. This is the first case. I've written x1 from the first equation, x2 from the second equation. And I start from 0, 0. I'll just show you what will happen. Okay. Just see the value of x1, x2 here. You will see what is the value of x1, x2 in the workspace. I start with x is equal to 0, 0, 0. Okay. Now I do this equation. Okay, that's a semicolon. So basically it is two equations. When I do run this equation once, I'm getting 1 minus 3. Okay. Again, I'm running the equation. I get 7, 3. Minus 5, 9. 19, 15. Minus 29, 33. You can see the value is increasing and the sign is also getting jumbled. And it's becoming really, really high values. Like how many ever times I run it, this solution is diverging. It's not giving me a easy answer. So the way you wrote the first way you wrote it will not give you a right answer because solution is diverging. Okay, now let's see the second way of writing the equation. Now the second way of writing the equation is this. Again, I'm writing x is equal to 0, 0. This is the second set of equation. You can see it is 4 minus 1.5. Let me run the equation once more. It became 2.5 minus 0.75. 3.25 minus 1.125. 2.875 minus 0.9375. 3.06 minus 1.03. 2.9688 minus 0.9844. 3.01 minus 1.0078. Again, it is close to 3. 2.99. Again, 3.00 minus 1.02. Running it again, 2.99. Running it again. See, you can see this value is around 3 comma minus 1. Now I am again running it multiple times. Now you can see the value is not changing. What is the value? It is 3 comma minus 1. How many other times I ran it? Now the value has settled at 3 comma minus 1. This is what I said the solution is converging. Earlier, when we did that, the solution was going on diverging over and over again. When you find it, the system is going that way, stop doing it. Okay. Now you can try writing the solution in a different like in the second way. Then you will find that the solution is converging. This depends on the system. Okay, which way you which way to write it and which will converge totally depends on your system. Okay, you can try any number of ways you want, and if you find the solution is diverging, stop it there, and that is not the right way to go. Okay, any doubts?
Ma'am, initially, can we guess which will diverge or converge? Like,
One simple way is what you can do is rearrange it in such a way that your solution becomes diagonally dominant. Okay. So here, if we are taking solution like this, if this is your matrix, you can see 1, 2, 1, minus 1. What is your diagonal? What is your entry? 1, 2, 1, minus 1. This is your entry, right? And from first one, you took x1, and second one, you took x2. Now, you try to make it diagonally dominant. That is, if you write it like this, if you exchange these two rows, 1, 1, 1, minus 2. Is this diagonally dominant? Because 2 is a large number and that came in the diagonal, right? And now you take x1 from here. Now you take x2 from here. This might work better than this. Okay, this might be the best.
okay.
Okay, try making it diagonally dominant, and then from the first one take x1, from next take x2, and so on. Okay.
Okay, ma'am.
Okay. Now next is called as a tridiagonal matrix. Like this is a certain kind of a matrix. In the main feature it is that it will only have elements in three diagonals. That is, a main diagonal entry will be there. Then there will be an upper diagonal, and then there will be a lower diagonal. So you can see there is a band. So this is a main diagonal. Then there is an upper diagonal, and then there is a lower diagonal. In this band, you will have some values. Okay, all the other entries. Apart from this, all the other entries you will see it is 0, 0, 0. Okay, so that is what is called as a tridiagonal matrix. Let me just clear it. Okay, so if it's a tridiagonal matrix, same as you did earlier, you can do Gauss elimination, you can do Gauss Seidel, or else you can do inverse of A multiplied by B. Like there are several ways of doing it. But in tridiagonal matrix, since a lot of entries are zeros, it is good that if you make use of the zeros, okay, the computation will be much more easier. So in chemical engineering field, you will see this tridiagonal matrix when you're trying to solve this equation, solve equations like this. When you have d square t by dx square is equal to gamma t minus 25, where t is a temperature. For example, this might be temperature of a road or something like that. Then you have an equation like this. And then you have to find for different values of x. That is, at different positions of the road, what is the value of temperature? Okay. So when you're trying to solve this problem, it will be given that one end of the road is at 100 degrees Celsius and the other end of the road might be a length of the road if it is 1 meter. Other end of the road is equal to 25 degrees Celsius. Now, between the road at different points, what is the temperature? That might be the question that you get. So if you're trying to solve this problem, the ideal way to solve this is using central difference formula. You'll be getting an equation like this. Okay, this d square t by dx square can be written like this, and that can be written as gamma t minus 25. If that is the case, okay,
Ma'am, that equation we will always use when trigonal matrices come.
no. I'm just telling you an example where you will observe tridiagonal matrix. This tridiagonal matrix is not only this. Okay, I'm telling you this is one of the ways you will be getting a matrix that looks like a tridiagonal matrix. Oh, this is an example for tridiagonal matrix. That's it. There might be several tridiagonal matrix, several other fields you will be seeing this matrices, but this is just an example, okay, of tridiagonal matrix. So you will be getting a problem like this. If you expand this problem properly, you will be getting a system of linear equations. Okay. So if you don't understand this part, that is completely fine because this is not a chemical engineering course. Okay. This is a mathematical course. So if you find this set of equations like this, the question is, how do you solve it? Okay. So first in this question, you can see T1 is in the diagonal. So basically, just for your understanding, I'm writing T1 here, okay? Rather than writing it here, I'm just writing T1 here and T11, okay? T1, then you have 0, T4, 0, T5, sorry, T5, and so on, okay? Like this also has so many elements. And finally, T11, I'm writing it here. Instead of writing it here, I'm just writing T11. So what happens? There is a main diagonal entry here. T1 is there, T2 is there, T3 is there, then you will have T4, T5, till T11 will be there. Main diagonal entry is there. This is the upper diagonal. This is the lower diagonal. You can see T1, T2. So basically, you will be just having three diagonal entries. This is T1, T2, okay, T3 till T11 is there. And here also you'll have some entries. Here also you'll have some entries. Apart from that, everything will be zeros. Okay, that's how this system will look like. Okay. Now, once you have this triangle entry, the first important job is you need to give the Matlab this entries. Whatever is this triangle entries are there, you need to code that in Matlab. So that might be a bit tricky, but I'll show you the code that is doing it, so you'll be able to understand. Just a second. Am I audible?
Yes, ma'am.
Okay, just a second. I have a problem with internet connection. Just give me a second. Okay, the first important thing is we need to enter the values into a triangle matrix. So first for that, the whole road problem, this is how you write it. There are like T1 to T11. Okay, basically what happened is, if we had a road, just give me a second.
Recording in progress.
Am I audible right now? I'm sorry, I'm using my tab to annotate, so there is a problem with the internet connection there. So the problem is, uh, yeah, thank you for waiting. So the problem is if we have a road like this, so what happens is in this problem, if we have a road like this, that road was divided into 10 intervals. Okay, 10 intervals means there will be 11 points. Okay, So this is how many intervals? 1, 2, 3, 4, 5, 6, 7 intervals. How many points you have? 1, 2, 3, 4, 5, 6, 7, 8 points. Okay. So if there are 10 intervals, there will be 11 points. So that is what we say n interval is equal to 10. This is alpha value, this is beta value. Alpha and beta comes from here. In the question it's given. Okay, the alpha and beta value is given. This is some constants whose values are given. Now you have to enter what is the value of this diagonal entry elements you have to enter. So let me just wait. Okay. So this is how you create the problem matrix. So I'm taking L11. So that is in the lower diagonal. The first entry is 0. Okay. There is only D11. Okay. There is no L11 and there is no U11. So if you see here, this is D11. Do you have a lower triangular matrix in the first row? No. Is there an upper triangular? No, it's not there. Okay. So L11 is equal to 0. U11 is also equal to 0. But D11 something is there. D11 is a coefficient of T1. The coefficient of T1 was 1. And what is B11? B11 is the first constant that you have. That is what? No, B11 is this 100. So you can see B11 is 100 and last B is 100. Rest in middle, if you have the B values that are beta. Okay, because your matrix looks like this. Your B matrix looks like this 100, beta, 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 so on. It will go up to 25. This is how your B matrix will look. Okay, and your A matrix looks like this. It will be 1, 0, 0, 0, 0, 0, and next is 0. Next is what? T1 is 1. Then you have minus 2 plus alpha. And T2 is 1. Then 0, 0. Then what do you have? Next entry is 0. You don't have T1 here. Next is 1. Then you have minus 2 plus alpha. Okay. In T3 position. T4 it is 1. And again, rest of the entries is 0. You have more zeros here. Okay. There are 11 variables. In next equation also, this 2 will be 0. You will have 1 here. You will have minus 2 plus alpha. And 1 will come. The rest of them will be 0. So this is how your matrix will look like. Okay. Going back. Okay. So Ln plus 1, comma 0 will be 0. Un plus 1, comma 0. That is the next row. First element is 0. And this is the upper row. Okay. This might be a bit tricky for you to understand actually. I'll just show you once I run this command. Like, because it's very important, rather than me explaining, it's very important that you write a pen and paper and you identify what these values are. So let me just run this code. Okay. You have, okay. Okay, when you run this code, I'll show you. This is what L looks like. Okay. This is, I've only done L11 and N plus 1 is what? L11. Okay. So then there is no first element is 0, else last element is also 0. Okay. And use first element is 0, use last element is also 0. So this part I have not modified right now. Okay. This is some, initially I have just defined it to be zeros. Okay. And now D11. So I'll show you U also, I've only declared the first two values. Rest are like automatically defined as zeros. This I'll modify later. Okay. Now I'll show you what is D. D, you can see the first value. This is the coefficient corresponding to T1. This is the coefficient corresponding to T2. Rest of the entries by default it is 0. This also I have to change. And B value, you will see it will be 100 is there, 25 is there. This values I have to change. Okay. Now what do I do? Let me go to the matrix here. So this is a lower diagonal. This is a lower diagonal. What is the coefficient? 1, 1. And so far, if you keep on writing the matrix, you will see all the lower diagonal elements are 1. And all the upper diagonal is T3 is T4. So this coefficient is the upper diagonal. That is also 1. So what do? I go to my Matlab code. I make all the entries from 2 to n. That is, this is 2 to n. 2 to n to be 1. U also I make it 2 to n to be 1. And D also 2 to n, it will be minus 2 plus alpha. Remember, if you go back, you will be seeing this was 1, T11 was 1, but all other diagonal entries has the coefficient minus 2 plus alpha. And all the betas in between, all the B's in between will have the value beta. Okay, and all the between B values will have beta. Now again, I'm running this. Now you will see what is UDL. Okay, U is this 0, 0, rest of the entries are 1. Diagonal entries, it is 1. Now this is minus 2 plus alpha. The last entry is also 1. And for lower 0, 0, between elements are 1s. Now for B, we'll see 125, and this is beta value. Because beta value, I had said it is minus 1. Okay, now I have made all the L, U, D, and B. That is upper diagonal, lower diagonal, and the main diagonal, and the B values. Once I've got all these 3 vectors, then I have to combine it so that it makes a matrix. So for that, already there is a code written. This is the matrix operations. If you remember in the first live session, we had seen that how to make a diagonal matrix, how to add this diagonal matrix, and all those things. We have done one question also in the assignment. So I'm not repeating it again. I'm just showing you the code here. If you want, you can just copy the code in Matlab and try see what is happening in each of the lines. Okay. What happens is when I run this code here, I'll be getting A like this. Okay. Basically using, you can see only L, you can see here. You can see this is what? This is your main diagonal. This is your bottom diagonal. That is L. And this is your upper diagonal. Okay, rest all the entries are zeros, right? Yeah. So like this, you made your tri-diagonal matrix. Once you have done the tri-diagonal matrix, so what you have to do is, this is the way you can solve the tri-diagonal matrix. You can just do UII is equal to, this is a formula, okay? Just like we had a formula for Gaussian elimination, this is a formula. You write UI is equal to UI minus the UI divided by diagonal element. You also write BI is equal to BI divided by the diagonal element. And the DI will also be divided by the diagonal entries. So basically what happens is, this is the Gauss elimination part only. That is the first row you had. So the first row you had, okay? The first row, whatever you had, has to be divided by your first diagonal element. That is, this was your pivot element, right? So using this, or what is this? This is DI. Initially, it will be D1. So based on this, you will be dividing everything here. What all things are there here? Here you have a diagonal entry. Here there will be upper diagonal, and there will be some elements here. But we are not worried about that because here it is all zeros. Now we have to only worry about B. Okay. So you divide everything by DI. So this becomes 1. Okay. This becomes UI divided by DI here. And this becomes beta I divided by DI. And DI divided by DI is always 1. Okay. So this is what you do first. Normalize by dividing by DI. Next is, once you have divided it, you have to, basically this is the Gauss elimination part only. Okay. Just a simplified version of it. So I divide that by the pivot element, that is DI. And then I have to do some row operations so that I can make the lower entry 0. So alpha is nothing but the lower diagonal value. Straight away you can write that. Okay. And then this straight away formulas are there. That is, the next lower diagonal value will be 0. The below value, basically D2. D2 is equal to D2 minus alpha times UI. Okay. So I don't know if I'm making it confusing for you. Just a second. This is D1. This is U1. This is D2. This is L2. Okay. And this is D3. This is L3. and you have U2. This is how it looks like. Then you go L4, D4, sorry, this is U3. Yeah, and U4 will be there. So on it will go. So first you divide this entire thing. Again, B1 is there, okay? Entire thing by D1. You divide the entire thing by D1. Okay, now this became 1. This also got modified. This also got modified. Now you have to divide L2 minus some alpha times. What is alpha? Here alpha is L2 divided by D1. This is your alpha value. This is your alpha value as per Gauss elimination. This value divided by this value. But this value I've always made it 1. So there is no point in doing this. It will straight away L2 itself. Okay, straight away L2 itself. So this is this command. Now you are subtracting L2 this row by alpha times this row. So automatically this became 0. So you can straight away without doing it itself, you can write this is 0. Now what is D2? D2 is equal to D2 minus alpha times U1. Right? D2 is equal to D2 times alpha times U1. So that is this. And what is B2? B2 is equal to B2 minus alpha times B1. What is there on the top? That is this equation. Okay. Like this, you can put a loop over all the rows, and finally you will be getting the simplified equation. This is basically the Gauss elimination only. So I'll just run this command. After that, I'm just making a matrix. After doing Gauss elimination, this is how it looks like. And it's clear. Okay, after doing Gauss elimination, this is what it looks like. You only have entries in the, all entries will be ones except the diagonal entries. That's how it looks. See, all entries are 1. This is 1, this is 1, this is 1, this is 1. Only the main diagonal, you will have some other values, rest are zeros. Okay, you can simplify it like this. And then what do? You have to do back substitution just like you did for Gauss elimination. Do back substitution as you did for Gauss elimination. You will be getting the answer. X values. I'll show you the X values. This is how the answer is. One end of the road is at 100 degrees Celsius. Other end of the road is at 25 degrees Celsius. In between, the temperature goes from 85, 74, 64, 56, 49, and it drops. Basically, it drops from 100 to 25. Okay. So this is an example with tridiagonal matrix. Have you understood how the calculations are going? Any questions? Okay, I'll just quickly show you some example. Yeah, ask.
Ma'am, in assignments like the alpha or values are like not given, so like not given in the sense the equations are just normal linear equations 4 or 5. So like finding alpha, we have to first find it manually and then put and
Yes,
then proceed.
yes.
Okay.
First, you have to manually find alpha. Yes, right. Because alpha, you already know what the relation is, right? You have to divide the particular value by the pivot element of that particular column. That formula
Okay.
that I showed you, alpha ij's
Yeah,
formula. Yes, you have to use that. Yes. Yeah. Now, I'll just quickly show you some example questions. So this is the question that you have. I know Gauss-Seidel method can be a bit tricky, but try to find the solution for this. Okay. Either like Gauss-Seidel method, I'll show you how to solve. But you can use this and try to find what is x1 value, x2 value, x4 value. Once you have got the, like right now use any method because we have time constraints. I'll show you the solution for this. Now tell me what is the answer for x1, x2, x3 in the chat box. And then, okay, the whole problem is a single problem. So I'll tell you, this is a Gauss-Seidel problem. Initial guess you have to take is 4, 3, 2, 1 for x1, x2, x3. So it goes iteratively. When do you stop this iteration? When the values, the consecutive values, xn minus x and minus 1. When in consecutive iterations, you're getting the same value of x. Now you have to do the same metrics. You have to do Gauss elimination. Okay. And in Gauss elimination, you have to tell me what this each element is. What is A11, what is A12, what is A13, and so on. Once you do Gauss elimination, also make sure that you save the value of alphas like this to get L. Okay, so these are the three problems. First is Gauss-Seidel. Same problem, you have to do Gauss elimination. And the same problem, while doing Gauss elimination, save your L matrix. Okay, so this is a question. I'll give you 5-10 minutes and then we'll discuss the answer. Please, if you have Matlab, try to do it in that, or else please try to do it using a pen and paper. And then we'll discuss the answers. Okay, I'll show you the answers because time is running out. So for Gauss-Seidel method, what you have to do is, there is like a loop, like the formula that I showed, right? So you should be able to code that formula. So that's the first part. So this is how you code that formula. This might be a bit tricky. So you have your A matrix, B matrix, then you make your augmented matrix. Right now I'm running it for 25 iterations. So my idea is either I can put it in a while loop in such a way that if the error, whatever error I'm finding, if that goes below the threshold, I stop the while loop. That is one way of doing it. Otherwise, what I do is I run the loop for many number of times. I calculate the error. When the error is like lower than a particular time, I can just put a break command. There is a command called as break in Matlab. I can break it out. Okay. So there are several ways you can do it. Now what I do is this is A, this is B, this is AB matrix. I have made the augmented matrix. This is my initial X values, initial guess X values. And this is number of equations. So there are like 4 equations, 4 unknowns. Okay. So error also, I'm just declaring it to be all 4 zeros. So far, this is the initial values I have. Okay. This is my A, this is my B, this is my augmented matrix, and this is my error values, all zeros initially, and this is my X values, initial guess. Okay. Now this is my loop. So I'm just declaring first X values to be the initial guess. So XOLD is my starting X value. Okay. And now this is the loop. This loop might be a bit tricky to understand. So what I can do is, so here you can see the new xk is actually num divided by askk. Num means the numerator value, that is this one, that is divided by askk. Now for the numerator value, just let's go back to the Gauss-Seidel formula. Okay, so Gauss-Seidel formula is like this: bk. What is bk? In the augmented matrix, the last element in a particular row, that is bk. Okay, so last element in a particular row, that is bk. So how do you find that? Go back to Matlab. As k means it will be a particular row. Nt means it will be taking in the last element of the particular row. So this will give you bk. As is the augmented matrix. The corresponding row's last element, that is bk. Now bk is there. Now we'll see what is this part. Going back. Okay, now we have to code this part. You remember this is a, k, j, where k is fixed. If a k here is fixed, k is fixed here, but j is looping from 1 to k minus 1. And that is multiplied by x. X also j is there. So that is x 1 to k minus 1. So this is a, k, j, where k is fixed, but the column values are changing from 1 to k minus 1. So let's see that. See here, if you see this code, AS, K is fixed, row number is fixed, but column numbers goes from 1 to K minus 1. That is multiplied by X. Again, it was XJ, which means J values will go from 1 to K minus 1. This is multiplied and subtracted as per the formula. Now next is, because this is subtracted, again, if this minus goes inside this bracket, again, this will become minus. A, K, J, again, K is fixed. J goes from K plus 1 to N. And here also XJ, J goes from K plus 1 to N. Let's see if that is coded correctly. AS, K, J goes from K plus 1 to N. X, J, where J goes from K plus 1 to N. So this is the numerator part. Now let us go to the denominator part. Denominator part is AKK. That is straightforward. So it has to be ASKK. See, it has to be ASKK. Now numerator divided by denominator, you will be getting corresponding SK. And you will run it for 25 times. I'll calculate the error accordingly. And the question, it has been mentioned that at iteration 4 and iteration 15, I have to type what the error value is. So let me type clear CLC I'll run this code. Okay. So the final error value is basically very small. It is very close to 0. At iteration 4, the error value was this is for x1, the error value is 0.59, x2, the error value was minus 0.735, and so on. At 15th iteration, you can see the error has dropped. Okay, from 0.5, it reduced to 499, 0.999, 2.0, and 2.0. Okay, at 15, this is the error. There will be 4 errors. One corresponding to x1, next corresponding to x2, next corresponding to x3, and next corresponding to x4. Okay, this is also like that. X4, this is for iteration 4, this is for iteration 15. Any doubts? Okay. Now next is the same question. You have to do Gauss elimination. I'm not explaining the Gauss elimination part again, but I can show you the answer so that once you do it, you can just compare your answers. This is the Gauss elimination code you have. Make the augmented matrix, find the pivot element, find alpha. Using alpha, you make the other element 0. Take the second pivot element, find alpha, make other element 0. Next pivot element, find alpha, make the other element 0. Okay. Running this, you'll be getting final AB to be like this. Okay. The question is, you need to enter what these entries are. That was a question. If I want to find the solution, okay, you have to do the back substitution. That part I have not done because the question has asked you the entries of the augmented matrix. Okay. Now going to the third part. Whenever you did this augmented matrix, what you have to do is corresponding alpha value has to be saved. I'll tell you one trick. You might have a doubt where this alpha values has to go to the corresponding entries of L. So what you do is, first you have to make an L matrix, an identity matrix. Okay. So first your L matrix looks like this. Okay. All entries are 1. Diagonal entries are 1. Now we need to make this entries. So basically, let me just annotate. Okay, now you have to enter values to this values. Okay, so for that, what you do is you see the alphas formula. This is AB21, AB11. What you have to do is you have to take this number. You have to take this number and this number. That is 2, 1. What you have to do is you take the L matrix and in the entry 2, 1, you place the alpha value. Sorry, alpha value. Okay. And the next alpha value, what you do is, let me just clear. Okay. Next alpha value is what? This is the next alpha value. So take the numbers 3, 1. And in L 3, 1, save the alpha value. And in next alpha value is 4, 1. And in L 4, 1, you save the alpha value. So that's how you enter it. Finally, when I run this code, you will be getting the lower triangular matrix to be like this. Is this clear? Sorry. Yeah. And one more thing is there. I think I made a mistake in explaining to you. Yeah. Okay. The entry is this element and you have to look at which is the pivot column. Okay. So for example, if this is the column that you're considering, you have to look at 3 and the pivot column is actually 2. So it is 3, 2. Okay. So let me clear it once again. So here you have to look at this number, and this number. And here this number and this number. And for here you have to look at this number and this number. Okay. The first number and the last number. This number and this number. So this is 3, 2. This is 4, 2. This is 3, 1. This is 4, 1. Is this clear? The numbers I pointed was wrong. It is this and this. Is this clear to you? And you might have a question, how did that come? So for that, I can just show you one more thing. See, L value is 2, comma 1. What is this? This is the second row, first column. Now let us look at what is the value for what is the formula for alpha 21. Formula for alpha 21 is, this will be, what is alpha 21? Okay, if we have alpha 2, comma 1, that is A 2, comma 1 divided by A 1, 1. So that is, you have to take this value, this value. So this is how this 2, 1 index came. Okay. Now taking the, let's take this value, alpha 3, comma 2. Alpha 3, comma 2 is actually A, let's go back. Yeah. A 3, 2 divided by A 2, 2, right? So this index, this index. Okay. That's how we write it. Any questions? I'll share the recordings of this lecture to you and also the PPT. So you guys can see it later also. And it will be there in the problem solving sessions of the course. If there are no other questions, I'll be ending the session and you may leave. Okay, thank you so much. I will be ending the session now.